Okay, I am here with Dr. William Gallagher, my friend and colleague, who is an adjunct associate professor of geology, environmental, and marine science at Rider. He was the assistant curator of the natural history collections and exhibits in the Natural History Bureau at the New Jersey State Museum. And whenever I run into him, I treat him as my personal paleontology tutor. So when I ran into him recently, I told him about the rhetoric of science class that we were teaching, and that we're sort of interested in the way scientists communicate science to other scientists, to the general population. And one of the things we had already talked about was the notion of normal science and revolutionary science as presented by Kuhn. And so I was aware of this new sort of paper because in the New York Times it reported that there was this sort of revolutionary restructuring of dinosaurs and sort of breaking up what had been a two-part division into a three-part division. So when I ran into Dr. Gallagher and asked him about it, he gave me some of his insights, and now he's going to share them with you. There you go.
Okay, so this is the paper in question. It came out in Nature recently. I downloaded this, of course, off the net. And it's entitled A New Hypothesis of Dinosaur Relationships and Early Dinosaur Evolution. If you want to hand me your diagram there. So this is what's called a cladogram. It's an attempt to show how organisms are related in terms of a family tree. So basically what they're talking about here is constructing a new family tree of dinosaur relationships. Who's related to whom? And of course, the old simplified tree was based upon the notion that there were two basic types of groups of dinosaurs based upon the hip structure. Kind of lizard-type hip structure called the Saurischian pelvis, and a bird hip structure called the Ornithischian pelvis. And the two groups based on this are Saurischia and Ornithischia, depending upon the hip structure. And the cladogram that came out that was kind of revolutionary for its time suggested that birds were in fact the descendants of small dinosaurs like our friend the raptors from Jurassic Park. And so this is the kind of cladogram that might have been drawn up in the past with a bifurcation at the level of Dinosauria into all the plant-eating, heavy-bodied, four-legged dinosaurs and some of the duck-billed dinosaurs called the Ornithischia, and then division into the Saurischia, including meat-eating dinosaurs, the big, slow, large, four-legged, long-necked sauropods, and coming off of that, the birds in the form of Archaeopteryx. So that was a prevailing hypothesis for many, many years. Now, a young fellow from Britain has proposed a more complex set of relationships, uniting the meat-eating dinosaurs with the Ornithischia, from which they were previously separated, and removing the sauropoda, the big, long-necked, heavy-bodied dinosaurs, from the theropods and putting them off in their own group, along with some obscure early types. And that's the critical key here. What's going on is this fellow has reevaluated the dinosaurs on the basis of some new discoveries and new interpretations of early dinosaurs. So a lot of this is based upon new discoveries. In that sense, it is revolutionary, but it's also a build-up over the decades of more information. A lot of the things that people have had to go on in the past with regard to very early dinosaurs are fragmentary specimens, bits and pieces. But as we go through this research, we get more and more good specimens from more and more field work. Now, there's some interesting things about this. It's not to be taken as the final word. This is an hypothesis. So every single one of these evolutionary diagrams, like this one, is a hypothesis, which means it's an idea that should be tested. And so there'll be further testing and discussion of this idea. It's an interesting, intriguing preliminary proposal, but by no means is it liable to achieve immediate acceptance across the board. So we have to keep that in mind. These are hypotheses. We can't see these things actually evolving in real time. What we're dealing with are skeletons of long extinct organisms. So we have to piece together as best as we can the evolutionary relationships from the anatomical features in the skeleton, and that's what all these are based upon. So they're based upon the selection of certain anatomical traits, like the anatomical traits that might be seen in this skull. It's a very open and airy skull. So the first thing you can notice about it is it's got a big antorbital fenestra. Now all these theropod dinosaurs possess this, and so do all the other dinosaurs. So this is a kind of anatomical feature that is characteristic of the dinosaurs and some other groups as well. Another thing that you can see are openings behind the eyes. This is the eye thing. So you see these temporal openings, and they help classify dinosaurs as diapsid reptiles. There are a variety of other openings. This is the anorbital fenestra, fossa, and this is another hole in this whole structure. So you have a very light, open, airy, bird-like skull. And that's one of the reasons why these kinds of dinosaurs are thought to be related to birds. They have a very open, bird-like kind of skull. So it's on the basis of these anatomical features, then, that we try to classify organisms. That's what he's done here. But of course, the critique of this kind of criticism is it depends on who's doing the choosing and what features they choose. So you can choose one set of features and emphasize that particular group of anatomical relationships, or you might be able to choose a different group. Now this fellow has chosen a great many different features. And of course what this represents is, of course, the triumph of big data. This is a big data set. Something like 74 different species of dinosaurs, 475 different anatomical characteristics. You do the math. That's a big matrix, and all that gets crunched through a computer program called TNT. Now the one we use here at Ryder to teach the students is called McClade, and that's a smaller, earlier version that runs on Apple. You need a big computer for this stuff. This is analyzing a lot of data very quickly, I might add, but it produces a vast number of different possible trees. This is just one of the trees that will produce. How do we select which tree is the most reliable? Which one we think might be the closest to what actually happened in nature? On the basis of parsimony, the idea that the simplest tree, the one that requires the least number of steps for all those evolutionary transformations involving these different anatomical characters to happen, we take that on the basis of parsimony, the simplest one. Now, he's done some clever things in here. He's put some of the earliest dinosaurs that ate meat in with the later plant eaters, the big heavy-bodied four-legged types. But part of the problem that he faces here is that all of the early dinosaurs seem to have been two-legged, fast, small, predatory types. And this confuses the issue as to precisely where the evolution among the early dinosaurs lies. He's cleverly reworded some of the initial kind of language about defining dinosaurs. For instance, Dinosauria was defined in 1842 by this British anatomist, Owen. And Owen identified Dinosauria on the basis of just a handful of specimens. At that time, there were just a few specimens from the south of England that he had to work with. But he very insightfully saw that they had a different hip structure from all modern reptiles. They had three vertebrae welded together in the hips. This is your lumbar region, your sacroiliac down here, where later on in life you may develop problems, right? So to put that in a practical human context. Well, these dinosaurs also got up on their hind legs and they developed bipedal locomotion. In that sense, they were ahead of humans. They were one of the first organisms to do this, and it may have been a key to their evolutionary success. And part of that whole evolutionary trend of getting up on two legs involved strengthening the hip region. So this is an additional one of these anatomical characters. And so what Owen said was the dinosaurs are the reptiles that have three vertebrae in the hip structure for strengthening up the back of the hip. And he cleverly reworded that as by saying, it's pretty complex, but he said the posterior most dorsal vertebrae becomes part of the primitive double sacral vertebrae series. That's the same thing. It's just been reworded in a different set of words for a new definition. So while this whole thing may stand the test of time, and it is an example of revolutionary science, it goes all the way back to 1842 and Owen's original diagnosis of the Dinosauria. And in fact, it was Owen who first put together the theropods with the plant-eating dinosaurs in a group he called Ornithocelida, just from the handful of creatures that he had available to him at the time. So in a sense, even though this seems revolutionary, it harkens back to the very beginnings of dinosaur science. And this is tradition and revolution, proceeding as new discoveries bring new information and data, and we have new ways of processing it today with computers.
Thank you very much, William. That was, you exceeded my expectations, and I'm sure the students will enjoy it.
I hope so.